tonight, somewhere inside the flood of radio energy washing across Earth, a narrow line appears. It is not bright enough to see in the night sky. It does not arrive as a voice. No one hears a greeting through a pair of headphones. At first, it is only a mark inside a computer display, a thin trace crossing a field of coloured noise while a radio telescope points toward a distant star. The line is unusually narrow. It moves slowly in frequency, and for several minutes it refuses to disappear. That does not mean humanity has found aliens. It means something much more dangerous to say too early. A telescope has found a candidate. By the end of tonight, you're going to understand what would actually happen after we detected a possible alien signal from the first suspicious line in the data, through the brutal process of proving where it came from, to the moment humanity might have to decide whether it should answer. Before we get started, if you love exploring the depths of space, please like the video, subscribe to the channel, and tell us in the comments where in the world you're listening from tonight. Now, let's begin. The modern search for extraterrestrial intelligence does not usually resemble the scenes shown in films. Researchers are not sitting in dark rooms waiting for a sentence to emerge from static. Radio telescopes collect enormous ranges of frequency at once. Computers divide those ranges into millions or billions of narrow channels. Algorithms then search for features that appear unusual compared with the natural radio sky and the technology surrounding Earth. The result is not silence. It is overload. Satellites transmit above the atmosphere. Aircraft cross telescope beams. Navigation systems broadcast precise timing signals. Radars sweep across wide regions. Mobile networks, spacecraft, computers, electrical equipment and distant transmitters all add energy to the radio environment. Some signals enter the telescope directly. Others arrive through side lobes, less sensitive regions around the main beam. Some reflect from objects in orbit. Some mix inside electronic systems and create frequencies that no transmitter intentionally produced. A genuine extraterrestrial signal, if one exists, must be found inside that human-made storm. The narrow line on the screen is interesting because many natural radio sources spread their energy across broader ranges of frequency. Stars, gas clouds, pulsars and distant galaxies can be powerful radio emitters, but an extremely narrow signal can suggest controlled technology. Suggest, not prove. Human transmitters are also narrow. The line's slow movement across frequency adds another clue. A transmitter moving relative to Earth experiences a Doppler shift. If the source rotates with a planet or travels in orbit, the received frequency may drift over time. Researchers search for that drift because it could reveal motion beyond the telescope. Yet Earth is moving too. The observatory rotates with the planet. Earth travels around the sun. The solar system moves through the galaxy. Satellites and spacecraft add their own velocities. A drifting line can therefore be exciting and completely ordinary at the same time. The software flags it. The first analyst checks whether the feature is strong enough to be real. Could random noise have produced a line that merely looks coherent? The observation may contain billions of opportunities for a false pattern to appear. A candidate that seems statistically rare in one small window can become inevitable when the entire search is considered. The analyst examines neighboring channels. Is the line isolated? Does it have weaker companions? Does it widen, split or pulse? Does it match a known transmitter? The exact time is recorded. So is the telescope's direction. The observatory checks its equipment logs. Were any transmitters operating on site? Did a receiver change mode? Did a clock lose synchronization? Did a maintenance system activate? Then comes one of the simplest and most powerful tests. The telescope moves away from the target. If the signal truly originates near the distant star, it should weaken or disappear when the main beam no longer points toward it. If the line remains, it may be entering through the instrument from somewhere nearby. The telescope returns to the star. The signal reappears. That is better. The dish moves away again. The line disappears. Then it comes back when the target returns. This on-source and off-source pattern can make a candidate extremely interesting. It can also mislead. A local transmitter may operate intermittently, A satellite may cross the beam during the target observation and move away during the control scan. A signal entering through a side lobe may change as the telescope turns. Timing alone can imitate direction, so the researchers repeat the sequence. Target. Control field. Target. Another control field. Target again. Each scan becomes part of a larger pattern. If the line appears only during the target observations, confidence rises. Not confidence in aliens. Confidence that the event deserves more work. At this stage, the researchers may not tell the public. They may not even tell most people inside their own institution. The reason is not necessarily secrecy. It is experience. Radio astronomy produces unusual candidates constantly. Almost all eventually return to Earth. A premature announcement can turn an ordinary interference event into a global claim that is almost impossible to retract completely. So the first responsibility is not to celebrate the signal. It is to attack it. The team checks satellite databases, aircraft records, spacecraft frequencies, military and civilian allocations, observatory electronics, weather conditions, computer processes. Anything that could place energy near the detected frequency becomes relevant. They search observations made before the candidate appeared. Was the line present on another day? Did it occur while the telescope pointed somewhere else? Did another project record the same frequency without noticing? They inspect both sides of the candidate. A human-made signal may produce harmonics or mixing products separated by regular mathematical relationships. The exciting line may be only one visible member of a much larger family. They examine its drift. Does the movement remain smooth? Does it change abruptly? Could the rotation of Earth explain it? Could the motion of a known satellite reproduce it? Every property that made the candidate interesting becomes a test that may destroy it. That is the strange discipline of the search. The researchers want the signal to survive. They must behave as though they want it to fail. Hours may pass, then days. The line remains unexplained. Its frequency is narrow. Its drift is measurable. Its timing follows the target more convincingly than expected. The researchers now possess something rare, but the language remains controlled. Not a message. Not a civilization. Not contact. A candidate. One feature in one telescope that has survived the easiest explanations. The signal exists. The instrument recorded it. Now the researchers must determine where it truly came from. And to do that, they will have to treat every machine on Earth as a suspect. The problem is that Earth is not merely noisy, it is saturated. Human civilization continuously fills the radio spectrum with transmissions created for communication, navigation, surveillance, research, and control. Many of those signals are regulated. A broadcaster is assigned one frequency range. A satellite service receives another. Aircraft, ships, emergency systems, and mobile networks operate within their own bands. But a frequency allocation is not a wall. Transmitters leak. Electronics are imperfect. Strong signals can appear outside their intended channels. Components inside a receiver can interact. Two frequencies may mix and create a third that no one deliberately transmitted. These unwanted products can be narrow, stable, and strangely placed. They can appear in a region that seems quiet enough to be extraterrestrial. The researchers begin with the obvious databases. Is anyone legally transmitting near the candidate frequency? Which satellites were above the horizon? Which aircraft crossed the region? Were there radar installations operating nearby? Could a deep space spacecraft have been communicating with Earth? A simple match may end the investigation quickly. Often, there is no simple match. That does not make the signal alien. It makes the interference harder to identify. The telescope itself is not a perfectly narrow eye. Its main beam points toward the target, but weaker regions around that beam can receive energy from other directions. A transmitter nowhere near the star may enter through one of these side lobes. As the dish moves between target and control fields, the geometry of those weaker regions changes. The signal can appear to follow the target even though it comes from the ground, a satellite, or another part of the sky. Engineers construct a directional model. They ask how the telescope responds to energy arriving from different angles. If a strong terrestrial transmitter lies near one side lobe during the target scan, the candidate's behavior may suddenly become ordinary. Then there is time. Satellites move. Aircraft move. Telescope beams move. A transmitter may activate for only a few minutes. During an on-source scan, it is present. During the off-source scan, it switches off. When the telescope returns to the star, it switches on again. The sequence looks meaningful. It may be coincidence. Researchers therefore examine the exact cadence. How long were the scans? How much time passed between them? Did the signal begin at the same point in every target observation? Did its strength change while the dish was stationary? A celestial source should behave consistently with the telescope's pointing and the physical motion of the source. A local transmission may follow a human schedule, a rotating radar, a satellite pass, or an automated process. The team compares the candidate with observations of other targets made before and after the event. A signal that appears only while the telescope points toward one star is more interesting than a signal found across the entire night. But search software can hide relationships. Suppose the interference drifts across frequency. During one observation, it lies at 982 MHz. Later, it has moved slightly. A search limited to the original frequency may miss it. The researchers must look for signals with related shapes and movement, not merely identical numbers. They widen the window. More lines appear. Most are weak. Some lie far from the candidate. A few drift in the same direction. Now the team asks whether they belong to one electronic source. This is where intermodulation becomes dangerous. Imagine two oscillators inside a piece of equipment. Each produces a stable frequency. When their signals pass through a nonlinear component, the system can generate combinations of both. Sums. Differences. Multiples. One of those products may land near the candidate frequency. If the oscillators drift because of temperature or voltage changes, the full signal drifts too. It can look like a transmitter accelerating in space. The researchers search for mathematical spacing between the candidate and nearby features. Does one frequency equal a combination of two stronger signals? Do several lines move together? Do they switch on and off at the same moments? A candidate that looked isolated may become part of an electronic fingerprint. The team also inspects the instrument chain. The signal passes from the telescope feed into amplifiers, converters, cables, digitizers, clocks, and computers. A fault at any stage may create a feature. The receiver may generate an internal tone. A clock reference may leak into the data. A cable connection may behave differently as the telescope moves. Software may duplicate, shift, or distort part of the spectrum. Engineers compare independent channels. If the telescope records two polarizations, does the candidate appear in both? Does it have the strength relationship expected from a source in the sky? If multiple receivers were active, did they all detect it? Can a test signal reproduce the feature? The rawest available data become valuable. Processed plots are easier to view, but every processing step changes the information. Filters remove noise, algorithms correct timing, software averages measurements. A mistake can enter anywhere. So the team works backward. From the final line on the screen, to the spectrum, to the digitized samples, to the voltage measured by the receiver. If the candidate exists before the main processing pipeline, one category of error disappears. Other categories remain. The source's name can create another danger. A strange signal from an unremarkable patch of sky may receive cautious attention. The same signal from Proxima Centauri, the nearest star to the Sun and host to known planets, carries enormous psychological force. The target feels meaningful before the evidence is complete. Researchers know this. They may still feel it. A nearby planetary system offers a story too powerful to ignore. The mind begins constructing the explanation ahead of the data. A transmitter on a planet. A deliberate beacon. A civilization only 4 light-years away. Those images can influence which details seem important. That is why analysis must be designed to survive expectation. The team separates the target's fame from the signal's properties. Would the candidate remain interesting if it came from an unnamed star? Would the same evidence be persuasive if no planet were known there? If the answer is no, the story may be carrying more weight than the measurement. The signal continues to survive. No registered transmitter matches it. No satellite produces the correct track. No obvious receiver fault explains its shape. The on-source pattern remains. The drift appears smooth. Still, the candidate has passed only tests performed around one observatory. The entire local environment may contain something the team has not recognized. A hidden transmitter, an unusual electronic product, a moving source absent from public databases. One telescope can investigate itself with astonishing precision. It cannot completely escape itself. For now, there is only a line with measurable properties and a long list of machines capable of producing it. One by one, those machines must be eliminated. And the more convincingly the signal survives, the more dangerous premature confidence becomes. Because history has already shown that a candidate can pass several of these tests, appear to follow one nearby star, and still be born entirely from technology on Earth. That warning became real in observations aimed at the nearest star beyond the Sun. In April 2019, the Parkes Radio Telescope in Australia, now formally known by its Wiradjuri name, Muriang, was observing Proxima Centauri. Proxima is only a little more than 4 light-years away. In astronomical terms, that is almost next door. It is a small red dwarf, dimmer and cooler than the Sun, and it is known to host planets. At least one of them moves through the region around the star where temperatures might allow liquid water under the right conditions. That does not make the system inhabited. It does, however, make it difficult to ignore. The observations were part of Breakthrough Listen, a large scientific search for signs of extraterrestrial technology. For many hours, Muriang collected radio data from the direction of Proxima Centauri. Those observations created an enormous archive filled with interference, background noise, astrophysical signals, and countless narrow features produced by human technology. Most of them were rejected quickly. Software searched through the data for signals with characteristics that might deserve closer attention. The initial process found millions of detections. Filters removed features that were too broad, too common, too obviously terrestrial, or present in observations where they should not have been. The number fell. Millions became thousands. Thousands became a smaller group of candidates. And eventually one signal refused to disappear. It was later called Breakthrough Listen Candidate 1, BLC1. The name sounds clinical because that is what it was supposed to be. Not a message, not a discovery, a candidate requiring investigation. It appeared near a frequency of 982 MHz. The signal was extremely narrow, occupying only a tiny slice of the radio spectrum. It also drifted slowly in frequency during the observations. Those were both interesting features. The signal was present during several periods when Muriang was pointed toward Proxima Centauri. During nearby control observations, when the telescope looked away from the star, the feature did not appear in the same obvious form. That was more interesting. A narrow band signal, a measurable drift. Present during target observations, apparently absent when the telescope moved away, and coming from the direction of the nearest stellar system to our own. This was exactly the kind of combination capable of creating a dangerous story before the investigation was finished. The signal had not been noticed live inside the observatory. It emerged later, during analysis of the stored data. A researcher named Shane Smith was examining the Proxima observations when the feature stood out from the surrounding candidates. The signal survived the initial filters. Then it survived further attention. Danny Price, Sophia Sheik, Andrew Siemion, and other members of the Breakthrough Listen team became involved in the analysis. Different researchers examined the data from different directions. They checked the observing sequence, the signal's drift, its frequency, its presence during target pointings, and its apparent absence in the control scans. For a time, BLC1 remained stubborn. That mattered because most false signals reveal themselves quickly. They appear in many directions, They match known satellite bands. They repeat throughout the observing session. They show no meaningful relationship to the target. BLC-1 was more difficult. It had enough promising features to justify serious work. And this is the point where popular retellings often become misleading. A research team investigating a candidate is not the same as a research team believing it has found aliens. The work becomes intense precisely because belief is not allowed to settle the question. The team began looking for ways to break the candidate. They searched data from other observing times. They examined wider regions of the radio spectrum. They changed filtering assumptions. They looked for nearby signals that might have been ignored because each one, viewed alone, seemed less interesting than BLC-1. The wider search changed everything. BLC-1 had appeared isolated when analysts focused narrowly on the candidate frequency, but surrounding data contained other signals with related behavior. Some appeared at different frequencies. Some had similar shapes. Some drifted in ways that resembled the original candidate. These signals were not obvious copies. The relationship had to be reconstructed, but as the team compared them, a family began to emerge. That family was the clue. Human electronics do not always produce one clean transmission at one clean frequency. Multiple oscillators can interact. Signals can mix inside electronic systems. Their combinations may generate new frequencies called intermodulation products. Imagine two ordinary tones entering a system that does not behave perfectly. The system may produce not only those two tones, but additional ones created from sums, differences, multiples, and combinations of the originals. Now allow those electronic sources to drift. Perhaps their temperatures change. Perhaps their power supplies fluctuate. Perhaps the devices switch modes. The mixed products drift as well. One of those products can land in a frequency range where no intentional transmitter is supposed to exist. It can appear narrow, it can move smoothly, it can look independent. And if the interference is intermittent, it may appear during target observations while remaining absent during the control scans by chance. That was the trap. BLC-1 was not a single mysterious visitor detached from Earth's radio environment. It was one member of a larger collection of related signals. Their frequency spacing, timing, morphology, and shared drift behavior pointed back toward local human technology. The exact original devices were not necessarily identified. They did not have to be. The family relationship explained the candidate's supposedly unusual features far better than an extraterrestrial transmitter did. The line from Proxima Centauri had come from Earth. That conclusion may sound disappointing. It was not. The team had taken one of the most compelling modern radio candidates and followed it until its disguise failed. The investigation demonstrated exactly why difficult verification matters. BLC-1 was not rejected because scientists were unwilling to consider an extraordinary possibility. It was rejected because they considered it seriously enough to test it properly. And the candidate had passed several tests. That is what makes the case so important. It was narrow. It drifted. It appeared during observations of an extraordinarily interesting target. It seemed to respect the on-source and off-source pattern. None of those features was enough. Even together, they were not enough. A false positive does not need to imitate only one expected characteristic of a technosignature. Under the right conditions, human interference can imitate several at once. That changes the standard for the next candidate. A future signal cannot merely look technological. It cannot merely come from the direction of a nearby star. It cannot merely disappear when one telescope turns away. It cannot merely drift at a rate that appears compatible with motion. It must survive a search designed with BLC-1 in mind. Researchers would look far beyond the candidate's exact frequency. They would search for hidden relatives. They would compare its behavior across the entire observing session. They would examine whether a group of terrestrial products could generate the same pattern. And even then, one observatory would remain vulnerable to its own local environment. One facility can examine itself with extraordinary care. It can test cables, clocks, software, receivers, transmitters, satellites, and side lobes. But it cannot completely escape the fact that every measurement passes through the same site. The same hardware, the same airspace, the same local radio landscape. BLC-1 revealed how far one candidate could travel through the verification process while remaining tied to Earth. The next decisive threshold would therefore have to come from somewhere else. A second telescope, different electronics, different software, different interference, perhaps another continent. Because if the same narrow drifting signal appeared independently at two distant observatories, both pointing toward the same star at the same time, the explanation would no longer be confined to one machine or one location. The candidate would not yet be proven alien, but it would have escaped the observatory that found it. A second telescope changes the problem completely. Until that moment, every piece of evidence has passed through one location, one receiver system, one set of cables, one software pipeline, one local radio environment. The original observatory can inspect itself with extraordinary care, but it cannot become independent of itself. So imagine that the candidate survives the first investigation. It remains narrow. Its drift cannot be reproduced by the receiver. No satellite track fits. No nearby transmitter explains the timing. The line returns when the telescope points toward the source and disappears when the dish moves away. Now the researchers contact another facility. They do not send a dramatic announcement. They send coordinates, frequency, bandwidth, drift rate, observation times, expected visibility. They may also provide an uncertainty window around every value, because the second observatory cannot search one perfect point. Earth is moving. The source is moving. The transmitter may be moving around a planet or star. During the delay between observations, the signal may shift. The second team receives the request and interrupts an already crowded schedule. A telescope operator checks whether the target is above the horizon. An engineer confirms that the appropriate receiver is installed. Analysts calculate how far the candidate frequency may have wandered since the original observation. Nothing about this guarantees success. The new telescope may be less sensitive. Its receiver may not cover the exact band. The target may rise only briefly. Weather may affect the system. The source may transmit intermittently. A beam that crossed Earth yesterday may have moved away by tonight. A failure to detect the signal therefore matters, but it does not always end the investigation. The second facility points toward the coordinates. Data begin accumulating. At first, the display contains the ordinary texture of a radio astronomy: broad background emission, instrumental features, passing interference, and thousands of narrow human-made signals. The analysis searches around the predicted frequency. Then, in this hypothetical confirmation scenario, a line appears. Not merely something similar. A narrow feature whose position and movement fall inside the range predicted from the first observation. That changes the status of the candidate. The first observatory sees it. The second observatory sees it. The facilities may be separated by hundreds or thousands of kilometers. Their receivers were built by different teams. Their clocks, cables, computers, and local interference environments are not shared. A loose connector at the first site cannot draw the same line in the second dataset. A local oscillator cannot cross an ocean. A software error inside one processing pipeline cannot automatically reproduce itself inside another system using different code. The candidate has escaped the machine that discovered it, but it has not escaped Earth. That distinction remains essential. Some human transmitters can illuminate enormous areas. Satellites cross the sky above multiple countries. Deep space spacecraft may be visible from several observatories. Powerful radar signals can travel far beyond their intended region. A transmission reflected from an aircraft, the ionosphere, or an object in orbit may appear at more than one site. Two telescopes seeing the same signal is therefore powerful evidence. It is not final evidence. The next question is directional. Did both instruments receive the energy from the same position among the stars? Each observatory has a different view of the sky. The target rises at a different time. The angle between the telescope and the source changes differently as Earth rotates. A satellite passing through one beam will not normally pass through the second beam in precisely the same celestial geometry. The teams compare timestamps. They correct their clocks against independent standards. They calculate the motion of Earth. They transform both observations into the same astronomical reference frame. If the signal truly originates near the target, the measurements should align after those corrections. Its frequency may not be numerically identical at both sites, because each telescope has its own velocity relative to the source, but the difference should match the motion that physics predicts. This is stronger than two lines that happen to look alike. It is one physical source telling a consistent story through two independent instruments. The signal should appear when the target lies inside each beam. It should weaken or disappear when the telescope moves away. Its drift should evolve in a way compatible with the changing motion of the observatory, Earth, and perhaps the transmitter itself. If the candidate repeats, its return should follow the sky rather than the workday of a local machine. Now a third observatory joins, then perhaps a fourth. The investigation becomes a campaign. Schedules change across several facilities. Engineers prepare receivers outside their normal observing plans. Teams divide the frequency range. One instrument watches continuously, while another records wider bandwidth. A large dish provides sensitivity. A smaller, faster telescope responds quickly when the signal returns. Instrument diversity matters as much as distance. Two facilities using the same receiver design may share the same hidden weakness. Two analysis groups using identical software may reproduce the same programming error. Strong confirmation therefore requires different routes through the evidence. Different antennas. Different electronics. Different processing code. Different institutions. Different people attempting to prove the candidate wrong. One analyst takes the raw voltage data and reconstructs the spectrum without using the Discovery team's software. Another searches every observation from the same day for weaker relatives. An engineer injects artificial test signals into the receiver chain to see whether the instrument can manufacture the observed drift. The candidate is not protected. It is attacked. Suppose a satellite is found near the line of sight. Orbital specialists calculate its predicted path and frequency movement. The timing misses. Suppose a spacecraft uses a nearby radio band. Mission records show whether it was transmitting and where its antenna was pointed. The geometry fails. Suppose a receiver effect is proposed. Engineers reproduce the relevant operating conditions in the laboratory. The artifact does not appear. Each ordinary explanation is converted into a prediction. Each prediction is compared with the measurements. This is how the exits begin to close. A network of separated dishes could establish that the signal follows one point in the sky. An interferometer could go further. Instead of using one large antenna, an interferometer combines signals from multiple antennas positioned across a site or across a much larger region. Tiny differences in arrival time allow the array to locate a source with far greater precision than a single broad beam. That precision could transform the case. A single dish observation might identify a region containing several stars, distant galaxies, and passing objects. Interferometric localization could reduce the uncertainty to a small area around one stellar system. If the source position shifts over time, repeated measurements might reveal orbital motion. Perhaps the transmitter follows a planet. Perhaps it circles the star aboard a spacecraft. Perhaps it occupies a stable point elsewhere in the system. The data may not be precise enough to distinguish those possibilities immediately, but localization gives them physical boundaries. The source can no longer be anywhere. It must be there. Still, precision is not intention. A transmission can be artificial without carrying a message. It can originate beyond the solar system without being aimed at Earth. It can emerge from a planetary system without coming from the planet that interests us most. Independent confirmation does not answer every question. It changes which explanations remain credible. At the beginning, the event was a suspicious line recorded by one telescope. Now it has survived different machinery, independent software, and geographic separation. It has appeared to people who did not discover it and have no reason to protect the original claim. The signal has crossed an important boundary. Local malfunction is no longer enough. One observatory's interference environment is no longer enough. One team's analytical mistake is no longer enough. Scientists are no longer asking only why the feature looks unusual. They are asking which physical source can place the same engineered-looking energy inside multiple telescopes. from the same position among the stars, while every familiar explanation keeps failing. And that is where the question becomes brutally difficult. How much evidence is enough? Not enough to make one researcher excited, not enough to persuade one observatory, not even enough to convince several teams that the signal is unusual. How much evidence would justify telling the world that technology exists beyond Earth? There is no single test that can answer that question. No frequency reserved for aliens. No pattern that nature is physically forbidden to create. No official percentage at which a candidate suddenly changes from mysterious to extraterrestrial. Science would not reach confirmation by finding one perfect feature. It would reach it through convergence, many independent pieces of evidence pointing toward the same explanation, while every serious alternative becomes harder to defend. The first requirement would be reality. The signal must genuinely exist in the measurements. It cannot be produced by a software error, a corrupted file, an incorrectly calibrated receiver, or a statistical fluctuation selected from billions of unsuccessful searches. That sounds obvious. It is not. When a search examines an enormous amount of data, rare-looking events will appear simply because the search has had so many opportunities to find one. A pattern that would seem astonishing in a small data set may become inevitable across millions of stars, frequencies, time intervals, and drift rates. Researchers therefore need to know how often their search process generates similar candidates by chance. They must ask whether the signal remains significant after accounting for every place they could have found it. Then comes localization. The evidence must connect the signal to a region of the sky with increasing precision. A broad single-dish telescope might initially place it somewhere inside a beam containing many possible sources. Follow-up observations could narrow that region. An interferometer could potentially reduce it further. The strongest case would not merely point toward a constellation or a famous nearby star. It would follow one stable celestial position. As Earth rotates, the telescopes would move relative to that position. The source would rise and set predictably. Its apparent frequency changes would correspond to known motion. Observatories separated across Earth would recover it from the same coordinates. The signal would behave like something in the sky, not like something attached to the observatory. Then comes repeatability. A signal that appears once and never returns may remain permanently ambiguous. It could still be real. A transmitter might have stopped. A narrow beam might never cross Earth again. A brief technological event might have lasted only seconds. But science becomes stronger when a result can be observed again. Perhaps the signal repeats every few hours. Perhaps it returns when the source reaches a particular position in its rotation. Perhaps it follows a schedule based on a planetary orbit. Perhaps it transmits a short sequence, pauses, and then begins again from the start. Predictability would matter more than simple repetition. If researchers can use earlier observations to forecast when the next transmission should arrive, and it appears at the predicted moment, the candidate becomes far more difficult to dismiss. Now consider bandwidth. A signal concentrated into an extremely narrow frequency range may suggest engineered transmission, because natural thermal processes generally spread energy more broadly. But generally is doing important work. Nature is inventive. Astrophysics has repeatedly produced objects that looked artificial before their mechanisms were understood. When pulsars were first discovered in 1967, their radio pulses arrived with such remarkable regularity that the possibility of extraterrestrial intelligence was briefly considered. The first source was informally associated with the name LGM-1, Little Green Men 1. The explanation turned out to be stranger in a different way. A rapidly rotating neutron star carrying a powerful magnetic field was sweeping radio emission across Earth like a cosmic lighthouse. The pulses were natural. Their regularity was real. Their discovery opened an entirely new class of astrophysical object. That history does not mean every candidate will eventually become a pulsar-like natural phenomenon. It means apparent design is not enough. A future signal would need to show qualities that are difficult to explain not merely through known natural sources, but through plausible unknown natural sources as well. Structured modulation could help. If the signal changed in a controlled sequence, switching between frequencies, phases, amplitudes, or polarization states, it might contain encoded information. But again, caution. Structure does not automatically mean language. A rotating object can create repeating patterns. Plasma processes can oscillate. Multiple natural cycles can interact and produce complex behavior. Human interference can generate modulation accidentally. The question is not whether the signal contains a pattern. The universe is filled with patterns. The question is whether the most economical physical explanation for that pattern requires a technological transmitter. That conclusion would grow stronger if the signal demonstrated several independent engineered properties simultaneously. Suppose it is narrower than known natural emitters. Suppose it arrives from one stable celestial location. Suppose multiple observatories detect it. Suppose its frequency drift matches a transmitter moving with a planet around the target star. Suppose it repeats predictably. Suppose the repeated sequence contains redundancy, internal correction, or mathematical organization unlikely to arise from an uncontrolled physical process. Suppose optical telescopes then identify brief flashes from the same system, synchronized with the radio transmission. No single item would carry the entire claim. Together they would form a chain. And even then, scientists would separate several conclusions that the public might compress into one word. The signal is unexplained. That does not mean it is artificial. The signal is artificial. That does not mean it is extraterrestrial. The signal is extraterrestrial. That does not prove biological life produced it. Technology may be operated by machines. The signal was produced by technology. That does not mean it was intended for Earth. The signal was intended for Earth. That does not mean it is friendly, hostile, or even understandable. Each step requires new evidence. Skipping those steps would create certainty faster than the data could support it. The scientific community would therefore become part of the experiment. The original team would release enough information for specialists elsewhere to challenge the analysis. Receiver engineers would search for hidden instrumental behavior. Radio astronomers would compare the candidate with known natural sources. Satellite experts would reconstruct orbital traffic. Signal processing researchers would test alternative filters. Statisticians would examine selection effects and false alarm rates. Some teams would try to reproduce the detection. Others would try to reproduce it as interference. This distinction matters. A strong scientific result does not emerge because everyone works together to defend it. It emerges because skilled people are given the opportunity to break it. Arguments would follow. One group might claim the celestial localization remained too broad. Another might identify a rare satellite geometry. A third might challenge the assumed drift correction. Someone might discover that a similar signal appeared years earlier in an unrelated observation. The candidate could weaken, or it could survive. If each proposed explanation made a clear prediction, researchers could test it. If a satellite caused the signal, its movement should follow a calculable path. If a receiver artifact caused it, laboratory tests should reproduce the feature. If a natural source caused it, observations at other wavelengths might reveal a corresponding physical process. If none of those predictions succeeded, the extraterrestrial technology hypothesis would not become true by elimination alone. But it would become increasingly difficult to replace. That is how the threshold would be crossed. Not with one triumphant measurement. With exhaustion. The candidate would pass through teams that did not want to be embarrassed, institutions that did not want to be misled, reviewers searching for weak points, and independent researchers building rival explanations. Slowly, the language would change. Interesting event might become high-priority candidate. High-priority candidate might become credible technosignature. And eventually, after enough independent evidence accumulated, a statement might appear that scientists have almost never had reason to write. The best available explanation is technological activity originating beyond Earth. That would still not explain the signal's purpose. It would not tell us who built the transmitter. It would not reveal whether the source was a living society, an automated machine, or the surviving instrument of a vanished civilization. But one boundary would have been crossed. Humanity would possess evidence that technology was not unique to this planet. The discovery, however, would not remain inside scientific language for long. By this stage, several observatories would be involved, data would exist in multiple institutions. Researchers, engineers, directors, reviewers, government contacts, and communications teams would know that something extraordinary was being examined. The scientific case might still be moving carefully. The information surrounding it would not. And before the evidence reached its final, cautious sentence, the world might already know that somewhere behind closed doors, scientists were trying to decide whether the silence had finally broken. The scientific case might still be moving carefully. The information surrounding it would not. By the time a candidate had survived several observatories, separate instruments, repeated observations, and months of hostile analysis, the number of people involved would have grown far beyond the original research team. Telescope operators would know. Receiver engineers would know. Observatory directors, data specialists, institutional lawyers, journal editors, outside reviewers, government science advisors, and communications staff might all know that an extraordinary claim was being prepared. Some would know only fragments. A telescope schedule had suddenly changed. A restricted observing campaign had begun. A particular star was receiving unusual attention. Researchers had cancelled public appearances. Data that would normally enter an archive had been temporarily held for verification. None of those details would prove anything. Together, however, they could create a shape large enough for the outside world to notice. And one screenshot might be enough. Perhaps someone photographs a frequency plot on a monitor. Perhaps a draft abstract appears briefly on a shared server. Perhaps a journalist learns that several major radio observatories have been following the same target. Perhaps a researcher sends a private message to a colleague who sends it to someone else. The candidate has not yet been formally announced. But the story has escaped. At first, the claims would probably be vague. Scientists investigating possible extraterrestrial transmission. Unusual activity at radio observatories. Signal detected from nearby star. None of those phrases would communicate the real uncertainty. Online, the distinction between a candidate and a confirmation could vanish almost instantly. Possible signal becomes alien message. Independent follow-up becomes multiple telescopes confirm aliens. Researchers cannot explain it becomes governments are hiding first contact. The first global battle may be over what is true. The original team would now face two competing dangers. Announced too early, and a terrestrial false positive could be transformed into one of the largest misinformation events in history. Remain silent too long, and rumors could harden into a public narrative that no later explanation can fully correct. The researchers would have to decide what they could responsibly say while verification remained unfinished. A carefully worded statement might acknowledge that an unusual candidate was under investigation. It could explain that such events are common, that most receive ordinary explanations, and that multiple facilities were conducting follow-up observations. Scientifically, that would be accurate. Emotionally, it might be useless. Millions of people would hear only that astronomers had not denied the alien story. News organizations would seek independent confirmation. Reporters would contact every observatory connected to the target. Former staff members would be asked to interpret partial technical details. Amateur analysts would download whatever data were available and publish conclusions before the teams closest to the instruments had finished checking them. Some of that outside scrutiny could help. An independent researcher might identify a satellite emitted from an early database. A radio engineer might recognize a known interference pattern. An astronomer with access to unrelated observations might find the same feature elsewhere. Open investigation can expose weak claims. It can also multiply weak claims faster than anyone can test them. The signal plot would begin circulating without context. Copies would be cropped, recolored, sharpened, and annotated. Some would be genuine, others would be altered. Entirely fabricated plots could appear beside the real one. Artificially generated audio might be presented as the sound of the signal, even though the original detection was radio frequency data never intended for human hearing. Fake messages could be attached to it. A mathematical greeting. A warning. A countdown. A translated phrase supposedly hidden in the transmission. The more emotionally powerful the invention, the faster it would move. And correcting it would be difficult because the real evidence might look far less dramatic. A thin drifting line. Confidence intervals. Instrument logs. Several cautious paragraphs explaining which possibilities had not yet been eliminated. Reality would be slower than fiction. Inside the research institutions, communication teams would begin preparing for several outcomes at once. If the candidate collapsed, they would need to explain why it had looked convincing and what finally exposed it. If the evidence remained ambiguous, they would need to describe uncertainty without turning uncertainty into permanent mystery. If the extraterrestrial explanation became credible, they would need to communicate the most consequential scientific result in history without claiming more than the data contained. That final task would be harder than it sounds. Imagine the verified conclusion is that a narrowband artificial transmission originated from beyond the solar system. That does not mean scientists have found living biological aliens. It does not mean a conversation has begun. It does not mean the signal contains a decipherable message. It does not mean the source knows Earth exists. Yet every one of those assumptions would appear in public discussion within minutes. The announcement would therefore need to repeat the limits as clearly as the discovery itself. What was observed? How it was detected? Which facilities confirmed it? Which terrestrial explanations were tested? Why a technological origin was favored? What remained unknown? The team would also need visual material that ordinary viewers could understand. A raw signal plot alone would not be enough. They might release diagrams showing how the source followed one celestial coordinate, how different observatories detected it, and how the frequency changed over time. They would have to show the chain of evidence, not simply state the conclusion. Meanwhile, researchers themselves could become targets of enormous attention. Their personal accounts might receive millions of messages. Some would be congratulatory, others would demand immediate access to the data. Some people would accuse them of fraud, others would accuse them of hiding information. Political groups, religious movements, commercial organizations, and online communities might attempt to recruit the discovery into narratives that existed long before the signal appeared. A scientist who had spent years studying receiver noise could suddenly be asked to speak about theology, national security, human destiny, and the psychology of alien beings. The pressure would be extreme. Institutions would need to protect the researchers physically and digitally. Contact information might have to be restricted. Observatory access could be controlled. Data systems would require additional security, not because the signal itself was necessarily dangerous, but because the evidence had become valuable, symbolic, and politically sensitive. The telescopes would continue observing through all of this. That part matters. While the world argued over a few leaked images, the actual source might still be transmitting. Every hour lost could mean information gone forever. The signal might change frequency. It might repeat on a schedule not yet understood. It might contain a sequence whose beginning had already passed Earth before anyone realized what they were seeing. So the scientific teams would need to maintain focus while the surrounding environment became louder. One group would monitor the target. Another would analyze earlier data. Another would inspect interference. Another would prepare public communication. Another would coordinate with outside observatories. The work would fragment because no single team could now carry the entire burden. And this is where secrecy becomes less realistic. Not because every scientist would rush to leak the discovery, because verification itself requires distribution. A claim this large cannot remain credible if only one institution is allowed to examine it. The evidence has to move to other telescopes, other analysts, other countries, and eventually to the wider scientific community. Each transfer increases trust. Each transfer also increases the chance of premature disclosure. The researchers may therefore lose control of the timing long before they lose control of the science. A rumor could become the largest story on Earth while the teams were still testing a mundane explanation. Or the candidate could be real, and the public might encounter it first through a distorted image posted by an anonymous account. Neither outcome would change the signal itself, but it would change the environment in which humanity tried to understand it. By now, the question would no longer be confined to whether the line came from another star. Another question would be growing around it. Could the evidence be released in a form strong enough to survive not only scientific criticism, but the noise of an entire connected planet. Because if the answer was yes, the next step would not be another private meeting. It would be an announcement. And from that moment onward, the signal would no longer belong only to the people who found it. The announcement would have to do something almost impossible. It would have to tell humanity that evidence of extraterrestrial technology had been found while making clear how little anyone still knew. There could be no room for a triumphant opening followed by corrections days later. No vague declaration that aliens have contacted Earth. No suggestion that a living civilization was waiting for a reply unless the signal itself supported that conclusion. The first official words would need to be narrower. Researchers have detected and independently verified an artificial signal originating beyond Earth. Even that sentence would be examined word by word. Detected would mean the signal existed in the measurements. Independently verified would mean more than one observatory, team, and instrument had recorded compatible evidence. Artificial would mean the best available explanation involved technology rather than a known natural process. Originating beyond Earth would mean terrestrial transmitters, satellites, aircraft, spacecraft, instrumental effects, and local interference had been investigated and could no longer explain the full observation. It would not mean the signal contained a greeting. It would not mean its makers were biological. It would not mean they were alive now. It would not mean they knew we existed. But the signal would no longer be a rumor. The announcement might begin at the institution that coordinated the original observation, but it could not remain the statement of one institution. Representatives from the independent observatories would describe what their instruments recorded. Receiver engineers would explain how equipment failure was tested. Signal analysts would show how the feature behaved across time and frequency. Astronomers would describe the celestial localization and the remaining uncertainty around the source. The strongest announcement would not ask the public to trust a famous scientist. It would reveal the chain of evidence. A diagram might show the telescope pointing toward the target, then moving away while the signal disappeared. Another might compare observations from facilities separated by thousands of kilometers. A frequency plot could show the same narrow feature drifting in compatible ways at different sites. Satellite tracks and known transmitters could be displayed beside the candidate, making clear why they failed to reproduce its behavior. The evidence would have to be visible enough for people outside the project to understand the basic logic. The signal appeared. It followed the sky. Other telescopes saw it. Ordinary explanations failed. And then the data would begin to move. Raw observations, calibration information, analysis methods, software, and processing code would be prepared for wider inspection. Some material might require careful formatting or removal of unrelated sensitive information, but the scientific core could not remain sealed indefinitely. A discovery this large would become stronger by leaving the hands of its discoverers. Independent researchers would download the files, they would rebuild the plots, they would run different algorithms, they would search for errors in timing, coordinate conversion, Doppler correction, calibration, and statistical analysis. Some would challenge the conclusion. That challenge would be necessary. A second wave of verification would begin outside the original collaboration, now involving researchers who had not participated in the discovery and had no reputational investment in preserving it. The candidate would face thousands of attempts to reduce it to something ordinary. If those attempts failed, confidence would deepen. Copies of the evidence would be stored in more than one place, not only on one observatory server, not only inside one country, not only under one institution's control. The raw data could be placed in geographically separated repositories. Analysis code could be versioned and preserved. Technical documents could record every transformation applied between the telescope's original measurement and the figures presented to the public. This would protect the evidence from accidental loss, cyber attack, political pressure, hardware failure, and simple institutional collapse. Human organizations are temporary. The discovery would need an archive designed to outlive the people who made it. While the files spread across Earth, the telescopes would remain fixed on the sky. The source might still be transmitting. That possibility would create immediate pressure. Observatories would revise schedules. Projects planned years in advance might lose time as instruments returned to the target. Facilities unable to detect the original frequency might search nearby bands. Optical telescopes could monitor the system for unusual flashes. Infrared instruments might look for unexpected heat signatures. High-energy observatories could check whether the signal coincided with any natural event. Most of those searches might find nothing. Nothing would still matter. If the signal existed only within one narrow radio channel, that would shape the interpretation. If another wavelength changed at the same moment, the physical picture could become much richer. Researchers would also widen the radio search. Was there a second carrier at a related frequency? Was the signal part of a larger transmission? Did it repeat after a fixed interval? Were there weaker components hidden below the noise? Had the beginning of the sequence already passed before anyone noticed? The original line might be only one fragment of something much larger, or it might vanish. A confirmed signal could stop immediately after the announcement, leaving humanity with a finite recording and no way to request a repeat. That possibility would make every minute of follow-up precious. The frequency itself might require protection. Human transmitters could contaminate the observation, especially once the signal's location became public. Curious individuals might deliberately broadcast near the same frequency. Hoaxers could attempt to imitate the original pattern. Commercial or government systems operating in nearby bands could interfere unintentionally. International telecommunications authorities might therefore be asked to coordinate temporary protections or restrictions around the relevant frequencies. Not because humanity owned the channel. Because once a signal becomes scientifically unique, human noise can destroy information that may never return. The announcement would also move into international institutions. Scientific organizations would be informed, government agencies would request briefings, United Nations bodies connected to the peaceful use of outer space could receive formal notification and technical documentation. This would not mean the United Nations suddenly took control of the discovery. There is no switch that turns a scientific detection into a unified planetary command structure. The first international role would likely be coordination, ensuring that the evidence remained accessible, encouraging continued observation, preventing unnecessary interference, sharing verified information across governments, beginning discussions about the consequences of any possible response. Those discussions would arrive quickly, but they would not be the first priority. The first priority would be the signal itself. What was it doing now? Was it repeating? Was it changing? Could its source be narrowed from a stellar system to a specific planetary orbit? Did the transmission reveal movement around a star? Could its frequency drift indicate the length of a day on the transmitter's world? Could periodic gaps reveal an orbit, an eclipse, a rotating beam, or an obstruction between the source and Earth? Every measurable change might contain physical information even if no message could be decoded. The signal could become a remote instrument for studying the place that produced it. Its stability might reveal the quality of the transmitter. Its timing might reveal the motion of the source. Its power could place limits on the technology required to make it detectable across interstellar space. Its duration could distinguish a continuous beacon from a brief event. This is where the emotional scale of the discovery would begin to change. During the announcement, the signal would seem like one line connecting one distant source to Earth. But soon, thousands of researchers would approach it from different directions. Astronomers would ask where it came from. Engineers would ask what machine could produce it. Mathematicians would search for structure. Linguists and information theorists would ask whether the variations carried symbols. Historians and social scientists would examine how human institutions were reacting. Legal scholars would ask who had authority over the data and any future transmission. The signal would remain physically narrow. The world around it would expand. And beneath the excitement, one uncertainty would begin to dominate. The announcement could establish that extraterrestrial technology existed. It could not establish that first contact was happening now. The signal may have crossed space for years, or decades, or centuries. The world that transmitted it might no longer resemble the world that received our attention. Humanity would be watching the source in the present night sky, but the technology speaking through the telescope could belong to the distant past. That is the first great reversal. The telescope is receiving the signal now. The transmission itself is not happening now. Light moves faster than anything else in the universe, but it does not move infinitely fast. Every radio wave requires time to cross space. The farther the source lies from Earth, the deeper into its past we are listening. If the signal came from Proxima Centauri, it would have traveled for a little more than 4 years before reaching us. That is the closest realistic case. Even there, the world that produced the transmission would already be more than 4 years older than the version visible in the data. A reply sent immediately from Earth would need another 4 years to arrive. The shortest possible exchange would therefore not resemble a conversation. It would resemble correspondence between worlds. A question leaves Earth. Years pass. An answer might begin its journey back. More years pass. And that assumes the transmitter is still operating, its makers are still listening, and both civilizations understand that communication has begun. Move the source farther away, and the meaning changes completely. At 100 light-years, the signal arriving tonight began its journey roughly a century ago. Its creators transmitted it before anyone on Earth had built the modern radio telescopes now receiving it. Depending on the exact year, they may have sent it before television became common, before humans entered space, or before our planet became strongly visible as a technological world. We would not be hearing their present. We would be hearing their history. A reply from Earth would take another century to reach them. If they answered immediately, the full exchange would require about 200 years, before allowing any time for analysis, decision, or message construction. No one who detected the first transmission would hear the response. No one who approved Earth's reply would hear it. The entire exchange would pass from one generation to another. Now place the source 1,000 light-years away. The signal would have left around a millennium before its arrival here. Its transmitter may have been operating while human societies on Earth lived in a completely different political, technological, and scientific world. The people or machines responsible for it would know nothing about the modern Earth receiving them. If they aimed the transmission toward the solar system, they aimed toward an ancient version of us. Perhaps they detected oxygen in Earth's atmosphere. Perhaps they identified a planet with liquid water. Perhaps they noticed signs of biology. But at that distance, any light they used to study Earth would also have been old. They could not have seen our current cities, satellites, radio networks, or spacecraft. The signal could have been sent toward a world they believed contained only simple life, or no technology at all. That possibility creates a strange asymmetry. We may receive a transmission from a civilization that never knew humans existed, and by the time our answer reaches them, they may have changed beyond anything encoded in the original signal. Civilizations do not remain frozen. Languages change. Governments rise and disappear. Technologies become obsolete. Species evolve. Machines replace older machines. A society capable of transmitting across interstellar space may transform itself on timescales far shorter than the distance separating it from Earth. The sender we imagine from the signal may no longer exist in the same form. The civilization could have expanded through its star system. It could have abandoned radio communication. It could have merged with artificial systems. It could have declined. It could have disappeared completely. The signal would not tell us which possibility was true unless its content somehow addressed the passage of time. This is why a confirmed transmission would not necessarily mark the beginning of first contact. It might be an archaeological artifact made of light, not an object buried beneath soil, not a ruined city, not a machine drifting through space. A pattern of electromagnetic energy carrying evidence that someone, somewhere, once built a transmitter. The artifact would have no physical surface. We could not hold it, visit it, or examine the machine that produced it. We would possess only the arriving radiation and whatever information survived the journey. That information might be extraordinarily rich, or almost empty. A stable carrier could prove technological activity while revealing little else. A repeating beacon might tell us that its builders wanted the signal to be noticed. A complex transmission could contain images, mathematics, scientific descriptions, or an attempt to establish a shared language. But none of those possibilities would show us the sender as it exists today. Even a detailed message would be historical. Suppose it described the transmitter's planet, biology, cities, and technology. By the time the message reached us, those descriptions could already be obsolete. Oceans may have changed, cities may have moved, political systems may have collapsed, the species itself may have altered its body or environment. We would be reading a self-portrait painted in the distant past. And the portrait may have travelled longer than the society it describes survived. There is nothing unusual about signals outliving their creators. Human radio broadcasts already move outward from Earth as expanding shells of faint energy. Early radar transmissions, television carriers, and planetary communications continue into space long after the people who produced them have died. Most become too weak to detect across great distances, but physically, the radiation continues. An extraterrestrial beacon built with sufficient power and directionality could remain detectable after its civilization stopped maintaining it. An automated transmitter might operate for centuries. A machine placed in a stable orbit could repeat the same sequence long after its builders vanished. The signal could therefore represent a living civilization, or a dead one, or a machine carrying out instructions that have lost their original meaning. A repeating transmission would not settle the question. Repetition proves that something continues to produce or replay the signal. It does not prove anyone is currently watching for an answer. A lighthouse can continue flashing after the coastline has emptied. An automated system can keep announcing a location after the society that created it has moved on. Even deliberate messages can become detached from their makers. Perhaps the civilization sends a vast library repeatedly, knowing that any receiver may discover it centuries later. The message would be designed not as a greeting to a known neighbor, but as a durable record. A statement that they existed. A map. A scientific archive. A warning. A memorial. Or perhaps the transmission was never intended as a historical object. Perhaps it was ordinary communication between machines in the sender's own system, leaking into space by accident. Earth might intercept one ancient fragment of a conversation whose participants are long gone. The most important discovery in human history could therefore begin with a profound absence. Evidence of intelligence. No living speaker. Evidence of technology. No functioning society. A message. No one waiting at the other end. That would not make the discovery smaller. In some ways, it would make it more unsettling. Humanity would know that intelligence had appeared elsewhere, but not whether intelligence endured. We would have one new example of technological life, and perhaps one new example of how easily its voice can become separated from its existence. The question would no longer be only whether we are alone. It would become whether technological civilizations overlap in time long enough to meet. The Milky Way is billions of years old. Civilizations may emerge at different moments, separated not only by distance but by entire eras. One could rise, transmit, and disappear before another develops the instruments required to listen. The galaxy might contain many voices that never become conversations. Signals crossing after the transmitters fall silent. Receivers built after the messages have already passed. Civilizations missing one another by centuries or millions of years. Detection would prove that the cosmic silence had been broken. It would not prove that anyone was still there to hear us answer. And before humanity decided what to send back, scientists would have to solve a more immediate problem. They would need to determine whether the signal was a message at all, or merely the distant exhaust of technology never intended for us. The distinction matters more than almost anything that follows. Alien does not automatically mean message. A signal could be artificial. It could originate beyond Earth. It could require technology to produce, and still have nothing to say to us. Human technology already creates enormous amounts of electromagnetic radiation without trying to communicate with extraterrestrial listeners. Radar sweeps through the sky. Spacecraft send instructions and telemetry. Navigation systems broadcast timing signals. Communication beams connect satellites, aircraft, ships, military systems, research stations, and distant probes. Most of those transmissions are meant for someone, but they are not meant for everyone who happens to detect them. An extraterrestrial civilization could produce the same kind of leakage. Perhaps its planet uses powerful radar to map nearby asteroids. Perhaps machines in orbit exchange narrow beams. Perhaps spacecraft communicate with stations around another moon or planet. Some fraction of that energy could escape the system and cross interstellar space. Earth might detect it by accident. In that case, the signal would not be a greeting. It would be overheard technology, a fragment of activity never designed for human understanding. That difference would shape everything scientists tried to do next. An accidental transmission may be brief. It may appear once and never return. It may contain information useful only to machines already sharing the sender's protocols, clocks, maps, and technical assumptions. Imagine intercepting a few seconds of communication between two unfamiliar computers. The exchange might be highly organized. It might carry enormous amounts of information. But without knowing the system that generated it, the data could look like meaningless variation. The signal could also be aimed somewhere else. Advanced transmitters may concentrate energy into narrow beams. Directionality makes communication more efficient because the power is not wasted in every direction. But a narrow beam also means most of the galaxy never receives it. Earth might detect the signal only because the beam crossed our position, while moving between 2 points in the sender's system. Perhaps a planet was communicating with a spacecraft. Perhaps one star system was transmitting toward another. Perhaps a rotating beacon swept across us for a few minutes before continuing into darkness. We would be standing in the path, not at the destination. Researchers would look for clues in the signal's behavior. How long did it remain visible? Did its strength increase and fade smoothly, as though a beam were crossing Earth? Did it repeat at regular intervals? Did its timing correspond to a rotating planet, orbiting spacecraft, or scanning transmitter? Did the signal return from exactly the same celestial position, or did it move within the source system? A transmission designed for local use might reveal the motion of the machines exchanging it. Its frequency could shift as a spacecraft crossed an orbit. Its timing might correspond to a planetary day. Periodic interruptions could occur when a moon, planet, or star blocked the path. The signal could tell us something about the system even if its content remained inaccessible. But now consider a different possibility. A beacon? A beacon does not need to contain a long message. Its purpose may simply be to announce that technology exists. It might transmit one narrow frequency continuously. It might repeat a short mathematical sequence. It might pulse according to a schedule that distinguishes it from natural phenomena. It might occupy a frequency chosen because astronomers across many worlds could recognize its physical significance. Such a beacon would be easier to detect than ordinary leakage because it could be built deliberately for interstellar range. Its transmitter could focus enormous power into a stable, predictable signal. It might repeat for centuries to maximize the chance that another civilization eventually notices. But a beacon still leaves crucial questions unanswered. Who built it? Why? Is anyone monitoring the responses? Is it an invitation, a marker, an experiment, or merely a monument? A beacon may be the cosmic equivalent of a lighthouse. It announces a location. It does not explain the people who built the coast. Researchers would search for repetition because repetition suggests design and offers additional opportunities for analysis. If the signal transmits the same sequence again and again, scientists can combine separate observations, improve the signal-to-noise ratio, and determine which features are stable. They can ask whether the pattern has boundaries. Where does it begin? Where does it end? Does one cycle repeat perfectly, or do sections change? A repeating carrier with no variation might function only as evidence. A repeating sequence with structured changes may contain information. Then comes the possibility that the transmission is a general broadcast, not aimed at Earth specifically, but designed for any sufficiently capable receiver. A civilization may transmit toward many nearby stars. It may operate a beacon that sweeps through a list of promising planetary systems. It may send a library repeatedly into the galaxy, accepting that the recipients and the date of reception are unknowable. A general broadcast would likely need to help unfamiliar listeners recognize what it is. The sender might include redundancy. Simple structures may repeat before more complex ones begin. One section could establish numbers, another could establish units of time or frequency. Later sections might build upon those foundations. But even that would not prove Earth was chosen. The transmission could have reached dozens, hundreds, or thousands of planetary systems. We might be one listener among many. A targeted signal would be different. If the transmission had been aimed specifically at the solar system, scientists would search for evidence that the sender knew where Earth would be when the signal arrived. Stars move. Planets move around stars. The solar system travels through the galaxy. A beam sent across decades or centuries must point not only toward where the target was observed, but toward where it will be when the signal completes its journey. If the transmission consistently tracked Earth's predicted location, that would be difficult to dismiss as accidental. Researchers might also ask whether the signal refers to local astronomical features. Does its timing correspond to the rotation or orbit of Earth? Does it use the frequency of a well-known atomic transition as a reference, then modify it in a way connected to our solar system? Does the sequence include information that could only have been selected by someone who had studied this region of space? The strongest evidence of targeting would be content that identifies Earth or the solar system in a physically recognizable way. But even then, intent remains uncertain. A signal aimed toward Earth may be an invitation. It may be a scientific experiment. It may be an automated survey response. It may be a warning. It may be a record intended for any technological species that eventually emerges here. The direction of a beam reveals where it was sent. It does not reveal why. And then there is the most dramatic possibility. An information-rich message. The signal may contain layers of changing structure. Its power, phase, frequency, or polarization could vary in controlled ways. Patterns may recur at multiple scales. Sections may contain clear repetition, internal checks, or predictable relationships that suggest deliberate encoding. At that point, humanity would know more than the existence of a transmitter. We would know that the transmission had been shaped to carry information. Still, information is not the same as language. A spacecraft telemetry stream contains information. A radar echo contains information. An encrypted military transmission contains information. A damaged file contains information. None is automatically understandable to an unintended receiver. The first analytical task would therefore be classification, not translation. Researchers would ask how many distinct states the signal uses, whether the changes are discrete or continuous, whether the same units recur, whether parts of the sequence behave like headers, timing markers, error correction blocks, images, or compressed data. They would search for hierarchy, small patterns inside larger patterns, repeated groups separated by stable intervals, simple sections followed by more complex ones. Any structure showing that the sender expected the receiver to learn how the message was organized. The strongest clue of deliberate interstellar communication might not be complexity. It might be patience. A signal built for unknown minds would probably repeat its foundations. It would provide reference points. It would tolerate errors. It would avoid relying entirely on local culture or hidden conventions. But we cannot assume another intelligence would design messages as humans would. Its communication may be optimized for machines. Its perception of time may be different. Its mathematics may be familiar while its representation is not. Its signal could contain a complete archive, yet appear almost random because the information has been compressed efficiently. Or the transmission may contain no message at all. That possibility must remain active even after technology is confirmed. A carrier can prove a transmitter exists. A drifting beam can reveal motion. A repeating pulse can reveal design. None necessarily carries a statement intended for us. Finding artificial light in the distance proves that someone built a lamp. It does not prove the lamp was switched on for Earth. So scientists would resist the urge to call the event a conversation. They would classify what the instruments had actually found. Leakage, local communication, a crossing beam, an automated beacon, a general broadcast, a targeted transmission, an information-bearing signal, or an artifact that fits none of those categories cleanly. The classification could change as more data arrived. A feature that initially looked like a simple beacon might reveal slow modulation across days. A one-time burst might repeat years later. A broad transmission might contain narrow embedded carriers. An apparently targeted sequence might turn out to be part of a survey scanning thousands of stars. Each answer would narrow the possibilities. Each answer could also expose a deeper limit. Because even if humanity became certain that the signal contained deliberate information, one enormous problem would remain untouched. How do you translate the work of a mind that has never shared a word, a world, a body, a history, or even a common way of sensing reality with you? The first mistake would be assuming that a recognizable pattern must carry recognizable meaning. It might not. Humanity could receive a transmission that is clearly engineered, deliberately structured and dense with information, then remain unable to understand a single idea inside it. The problem begins before translation. Researchers must first discover where one meaningful unit ends and the next begins. Imagine that the signal contains a repeated stream of two distinguishable tones. A high tone, a low tone. They arrive in a long sequence, broken occasionally by silence. That sounds promising, and two states could represent binary digits. High might mean 1, low might mean 0, or the assignment could be reversed. The tones may not represent digits at all. They could mark the edges of larger symbols. The silence may be punctuation, synchronization, equipment downtime, or the moment when a rotating beam points away from Earth. Nothing comes labeled. The first analytical group divides the stream into equal intervals. A second group measures the duration of every pulse and discovers that some are slightly longer. Another notices that the gaps repeat according to a larger rhythm. The same transmission now supports several possible alphabets. Researchers search for boundaries. Does one short sequence recur before every long block? Does the signal reset after a fixed number of units? Do some patterns appear only at the beginning or end of a transmission cycle? A repeated cluster might behave like a header in a digital file. It could identify the message type, provide timing, or tell the receiver how the next section is organized. Or it could be a mechanical rhythm produced by the transmitter. The distinction must come from prediction. Suppose one proposed header is followed by blocks of exactly 10,000 two-state units. The pattern returns before each block and never appears inside them. That regularity gives the interpretation strength. Now the teams ask what 10,000 units contained. Placed in one line, the data look almost random. Placed into a 100 by 100 grid, several large regions appear. One corner repeats a simple pattern. The center contains symmetrical forms. The final rows look like checks on the information above them. The image is not yet a picture. It is only an arrangement with more structure than most alternatives. Independent teams must recover it without being shown the expected result. Analysts test 50 by 200, 80 by 125, and every other reasonable factorization. Most produce noise. The 100 by 100 layout repeatedly reveals organized relationships. That does not prove the sender intended an image. But the hypothesis now makes useful predictions. If the next block uses the same grid, corresponding regions may serve similar functions. A section interpreted as an error check should identify damaged rows. A supposed orientation marker should remain stable. The next transmission arrives. Again, 10,000 units. Again, the same border pattern. Again, information aligns when placed into the same dimensions. Now the case is stronger. Researchers begin to understand the container before understanding the content. This is how decoding may advance, not through one brilliant translation, but through layers of constraints that gradually remove bad interpretations. Statistics come first. Some units occur more often than others. Certain sequences always appear together. A small group predicts what follows. One section is highly repetitive. Another contains few obvious patterns and may be compressed. A third appears several times with tiny changes, as though the sender were transmitting related examples. The message has architecture. Error correction could reveal part of that architecture. Interstellar signals weaken across distance. Noise damages individual units. Plasma between stars can distort the arrival time of different frequencies. Earth's own technology adds contamination. A sender expecting those problems may repeat information or include relationships that allow missing pieces to be reconstructed. Perhaps every row of the 100 by 100 grid ends with a check value. Researchers deliberately remove several units from a test copy. Using the suspected checks, they restore them. Then they compare the reconstruction with an undamaged repetition of the block. It matches. That is a real payoff. The team has not translated the message, but it has learned one rule used to protect it. Each recovered rule makes the remaining data less arbitrary. Mathematics offers another possible bridge. A short sequence may represent prime numbers 2, 3, 5, 7, 11. If the encoding is unambiguous, that pattern would be difficult to explain through an uncontrolled astrophysical process. It could establish that the sender expects ordered quantities to be recognized. Yet mathematics does not arrive free of representation. Are pulses counted directly? Are numbers written in binary? Does one long tone separate values? Is the sequence being read in the correct direction? The meaning of prime number may be universal, but the path from radio energy to that concept is not. Suppose the repeated opening successfully establishes counting. Later blocks may introduce ratios. One sequence doubles, another halves. A third corresponds to the frequency of a known atomic transition. That transition could define a shared unit of time. From time, the sender might construct length through the speed of light. From length, it could establish the dimensions of objects or distances inside its planetary system. This remains a hope, not a guarantee. Mathematics can anchor physical quantities. It does not automatically explain experience. Consider the structured grid again. After months of analysis, one region appears to contain several nested circles. Another contains lines radiating from a central point. A human observer might call it a planetary system. That interpretation may be right. It may also be projection. The circles could represent energy levels, biological structures, probabilities, or a diagram from a sensory system humans do not possess. Which direction is up? Does a dark cell indicate absence, low intensity, negative value, or simply one state in an abstract code? Does apparent size represent physical scale? Human beings bring hidden visual conventions to every image. We understand perspective because we have spent our lives seeing distant objects appear smaller. We recognize shadows, edges, and faces because our brains evolved inside a particular environment. Another intelligence may not use those conventions. Its message could be optimized for magnetic perception, chemical gradients, pressure waves, or machine sensors. Even an honest self-portrait might fail to look like a body. Time creates another barrier. Humans organize events through seconds, days, seasons, lifetimes, and generations. Those units emerge from our planet and biology. The sender may inhabit a world with no day-night cycle. It may operate through machines whose useful processes last microseconds or millennia. A pause we read as punctuation could represent a long internal calculation. A rapid sequence may compress centuries of observation. Culture forms the deepest wall. Meaning is not contained entirely inside symbols. It depends on shared experience. A diagram may establish the chemical structure of water. It cannot automatically transfer what an ocean means to a species that evolved beside one. A symbol may identify an individual body. It cannot explain whether individuality carries emotional, legal, or social importance to the sender. Alien concepts may be built from experiences no human has had. Memory distributed across many bodies. Identity copied between machines. Navigation through magnetic structures. A social decision lasting thousands of years. There may be no short translation because there is no human equivalent. Researchers would therefore work in layers. Signal states. Timing. Repeated blocks. Error correction. Numbers. Units. Physical relationships. Only after those foundations survive repeated testing could richer meanings be proposed. Every claimed interpretation must show its path. Not simply, this symbol means a planet. The analysts must demonstrate how the symbols were divided, how the grid was identified, why the dimensions were selected, what established the scale, and why alternative readings explain less of the transmission. A useful translation predicts something outside the passage that created it. If one section defines a number system, that reading should make later quantities coherent. If a pattern identifies hydrogen, related ratios or frequencies should appear elsewhere. If one grid orientation is correct, future grids should use the same convention or contain a clear signal that the convention has changed. Advanced software would test millions of arrangements and models. Artificial intelligence could identify hidden repetitions no human team would notice. It might discover that sections separated by weeks are mathematically connected. But computational power does not remove assumptions. Ask a system to find images, and it may produce image-like arrangements. Ask it to find grammar, and it may divide the data into language-like units. The output still needs independent evidence. No translation becomes credible merely because a powerful machine generated it. Years could pass. The transmission might be copied perfectly, stored in archives and examined by thousands of specialists. Humanity could understand its container, repair damaged blocks, identify its numbers, and reconstruct several physical diagrams. The central meaning may still remain closed. Pattern is not meaning. Information is not understanding. That frustration would create a new struggle. Once competing translations begin to appear, the question is no longer only which one is correct. It becomes who controls the data, who releases the tools, and who gains the power to tell the world what the signal supposedly says. That power would not belong automatically to the people who discovered the signal. They may control the telescope that recorded it. Their institution may operate the servers containing the first complete copy. Researchers may deserve credit for identifying and verifying the candidate. None of them created the transmission. The signal crossed interstellar space without recognizing laboratory walls, national borders, commercial contracts, or scientific priority. Yet every attempt to understand it would pass through those human structures. Consider the first morning after the public release. An observatory uploads a calibrated dataset, analysis code, and technical documentation. The raw recording is enormous, far larger than the simplified signal file circulating through the media. Universities begin downloading it. So do national laboratories. Private technology companies redirect computing clusters toward it. Amateur researchers form online groups. Intelligence agencies almost certainly preserve their own copies, even if they say nothing publicly. The evidence has become widely available. Access is not yet equal. A small research group may possess the data but lack the storage required to hold every observation. Another team may have enough computing power but not the specialized knowledge needed to interpret the telescope's calibration. A company may process the entire archive in hours while a university requires weeks. The data are open. The ability to extract meaning remains concentrated. That imbalance could shape the first public interpretation. Imagine that one heavily funded team announces a breakthrough. Its software has reconstructed a structured image from the signal. The institution holds a press conference. A large diagram appears behind the speakers. Within minutes, the image is copied across news networks and social platforms. It becomes the face of the discovery. Another group examines the method and notices a choice buried early in the pipeline. The first team divided the signal into blocks using one timing interval. A slightly different interval produces no image. A third team finds that several grid sizes generate equally suggestive forms. A fourth argues that the original reconstruction amplified damaged data in a way that created false edges. The dispute is scientific. Publicly, it may look like concealment or chaos. Millions of people have already seen the first picture. Later corrections compete against an image that is simple, memorable, and emotionally powerful. The transmission has not changed. Human memory has. This is why access must include reproducibility. A team claiming to decode part of the message should publish the meaningful steps between the raw recording and the final result. How were symbols separated? Which damaged intervals were removed? What assumptions established the timing? Why was one grid selected? Which section served as error checks? Can another group begin with the raw data and recover the same structure? The analysis should be more than downloadable. It should be inspectable. A researcher on another continent ought to be able to rerun the code, replace one assumption, and see how the conclusion changes. That process is slow. It is also the defense against one interpretation becoming authoritative merely because it arrived first. Scientific priority would still create pressure. Careers can be built around being the first to decode a section. Institutions compete for prestige, students and funding. Companies may see opportunities in specialized software, education, media, or advanced signal processing tools. Governments would have different concerns. Suppose a section appears to describe a physical process unfamiliar to current science. The interpretation could be wrong. It might be incomplete. It may require conditions unavailable on Earth. Even so, national security agencies would ask whether the information could produce energy, materials, propulsion, or weapons. A public dataset does not guarantee public analysis. One government could download the same files as everyone else, then classify the models its laboratories build from them. Another state would assume that something important had been discovered. It might establish a secret program of its own. The result could be scientific openness on the surface and strategic competition underneath. No elaborate conspiracy is required. Ordinary incentives are enough. Fear of falling behind. Fear that another country has interpreted the signal first. Fear that public release could expose a dangerous technique. Fear that secrecy itself will surrender trust. The signal could produce cooperation and suspicion at the same time. A practical conflict might begin with something much smaller. An independent team requests access to the unprocessed voltage recordings rather than the calibrated public files. Observatory managers hesitate because the raw archive contains unrelated emissions, proprietary engineering information, or details about the instrument's vulnerabilities. The researchers accuse the institution of withholding the real evidence. The institution argues that it is protecting systems and preparing the files responsibly. Both positions may contain truth. Open science does not mean every byte can be released instantly without technical or legal review. But unexplained delay creates a vacuum, and vacuums fill with stories. The solution would require staged transparency. First, release the data necessary to reproduce the detection. Then publish calibration records, processing documentation and known limitations. Preserve the original raw files under trusted international custody so that independent experts can inspect them, even if unrestricted public distribution is temporarily impossible. Record every transformation, every filter, every deleted interval, every correction. The archive must make it possible to move backward from a published result to the original measurement. Ownership of the files would still exist in law. Authority over meaning must remain contestable. Language adds another layer of control. The first major papers may be written in English or another dominant scientific language. Press conferences are translated. Technical uncertainty moves through dozens of news systems. Evidence of deliberate structure becomes confirmed message. Consistent with artificial origin becomes scientists identify alien civilization. Unable to exclude becomes experts believe. Humanity faces two translation problems. The first is the extraterrestrial transmission. The second is explaining our own analysis to one another. Different cultures would not react through one shared framework. Religious traditions, political movements, philosophical schools, and local communities would interpret the discovery through their own histories. Some might treat it as confirmation of earlier beliefs. Others might reject the scientific conclusion. Many would accept the evidence while disagreeing about what it means for human identity. That diversity is not noise surrounding the real response. It is part of the response. No institution stands outside history and culture. Even an international panel must choose who enters the room. Which scientific disciplines are represented? Which countries? Which languages? Which communities normally excluded from global technical decisions? Are private observatories treated like national facilities? Do the discoverers receive greater authority because they understand the data? Can panel members publish dissenting interpretations? Who explains uncertainty to the public when disagreement remains honest? These choices affect which translation gains legitimacy. And the stakes rise sharply when interpretation turns into action. It is one thing to believe that a pattern describes a star map. It is another to aim a transmitter according to that map. It is one thing to suspect that a sequence asks a question. It is another to answer it. The people controlling the most trusted interpretation could shape the decision that follows. Control the data, and you influence which conclusions become visible. Control the interpretation, and you influence what Earth believes it has been asked. Control that belief, and you may influence whether Earth responds. By now, copies of the original signal would exist across the planet. No single laboratory could erase them. No government could easily claim exclusive possession of everything the transmission contained. Distributed files, however, do not automatically produce distributed power. Humanity could receive one coherent signal while remaining divided among nations, companies, institutions, cultures, and individuals. Eventually, those disagreements converge on a question that no software pipeline can solve. Someone may own a transmitter powerful enough to reply. Someone may possess a proposed translation. Someone may already have written a message. But who, exactly, has the right to speak for Earth? Earth has no elected voice. There is no president of the planet. No parliament represents every human community. No institution possesses unquestioned authority to make a decision for all nations, cultures, and future generations. Yet the physical ability to transmit a reply could belong to a surprisingly small group. A government may control a powerful radar. A scientific facility may operate a large dish. A private organization could finance a transmitter. A wealthy individual might purchase time on existing infrastructure. The technical command can be concentrated. The consequences are claimed to be planetary. That contradiction would enter the room before any message was written. Current post-detection principles developed within the CT community favor verification, open dissemination, and international consultation before a reply. They provide guidance for responsible behavior. They do not create a world government. The documents are not a universally binding planetary law, and the broader reply procedures proposed over the years have not produced one accepted mechanism capable of authorizing humanity's first response. The signal could arrive before political legitimacy has been built. Picture the first international consultation. A large conference room. Delegates wearing headsets. Scientists presenting a frequency plot on one screen and the source coordinates on another. Legal advisors comparing voluntary protocols with national communications law. Engineers explaining that the transmitter could be ready within months. No one in the room doubts the importance of the decision. They may disagree about almost everything else. One model gives authority to the discovering team. Its members understand the evidence. They know which parts of the signal are secure and which remain uncertain. They may have immediate access to the equipment capable of transmitting. But expertise is not representation. Finding the signal qualifies scientists to describe how it was detected. It does not automatically authorize them to decide what 8 billion people should reveal about themselves. A second model places responsibility with the nation where the observatory is located. That government already regulates radio frequencies, major infrastructure, and international communication from its territory. The arrangement is practical. It is not planetary. The signal did not arrive for the land beneath one telescope. Another civilization may interpret any deliberate response from Earth as the voice of the whole planet, even when most of humanity never approved it. A third possibility creates an international scientific committee. Astronomers, engineers, mathematicians, linguists, information theorists, and experts in communication could assess the evidence and determine whether a proposed reply is technically coherent. They could answer questions such as, have we identified the transmission frequency correctly? Can we predict where the source will be when our message arrives? Does the proposed encoding rely on assumptions the receiver may not share? Would the signal be detectable at the target? Those are essential questions. They are not the whole decision. Should Earth reveal biological information? Should it include human history? Should the message describe conflict, inequality, or environmental damage? Should it claim to represent one civilization when humanity does not operate as one? No telescope can settle those issues. A broader process might pass through the United Nations, including the Committee on the Peaceful Uses of Outer Space, the General Assembly or a specially created international body. Governments could debate the decision publicly. Scientific organizations could present evidence. Legal specialists could examine jurisdiction. Philosophers, historians, artists, religious communities and civil society groups could contribute to the question of representation. That would increase legitimacy. It would also consume time. Months may pass while participants argue over membership. States may demand veto power. Some governments may refuse to recognize a process they believe gives rivals too much influence. Others may insist that no signal leave Earth without broad consensus. During the debate, the source might continue transmitting, or it might stop. Suppose the incoming signal repeats every 6 months, followed by a long interval of silence. Some researchers interpret the silence as a listening window. The interpretation is uncertain. The next window approaches anyway. Inside the technical facility, engineers calculate when the target will be visible. A transmission plan lies ready on a secure system. The antenna must begin moving at a specific time to reach the correct pointing angle. Inside the international chamber, delegates are still negotiating the wording of the decision. The physical universe does not pause for the meeting. Do they wait for wider agreement and risk missing the suspected window? Or authorize a limited response through institutions that represent only part of Earth? Neither choice is neutral. A global public vote sounds more legitimate. Let everyone decide. But the practical questions appear immediately. Who organizes it? How are identities verified? How are people without reliable internet access included? Which languages are used? What exactly is placed on the ballot? Should Earth respond? Is not enough. A meaningful vote would need to address the content, timing, power, direction and authority behind the transmission. Most voters would be choosing while expert disagreement remained. Public opinion could also be shaped by fabricated translations, political campaigns, and fear. A vote expresses preference. It does not design a technically valid interstellar signal. Another approach requires silence until broad consensus forms. This protects against an impulsive decision. It creates time for additional decoding and keeps one institution from claiming authority it never received. Silence is still in action. If the signal was aimed deliberately at Earth, no reply communicates something, even if the sender cannot know the reason. Perhaps it communicates caution. Perhaps division. Perhaps nothing at all because no one is listening anymore. Complete silence may also be impossible to enforce. A private organization does not require the consent of the entire planet to radiate energy toward a star. A state may decide that scientific or strategic interests justify acting alone. A group may believe that waiting for universal agreement means waiting forever. International consultation can establish norms. It cannot physically control every transmitter on Earth. That is why the authorization chain matters. At the facility chosen to send an official response, no single person should be able to improvise the final act. The target coordinates would be independently checked. The message file would be cryptographically verified against the publicly approved version. Engineers would confirm frequency, power, beam width and transmission schedule. Legal and institutional authorization would be recorded. More than one operator might be required to release the command. The process would resemble the control of other irreversible high-consequence technologies, not because the message is assumed to be dangerous, but because it cannot be retrieved after transmission. Even a careful technical chain does not solve legitimacy. The consultation must answer 3 separate questions. Should Earth reply? Who may approve the reply? What can the message honestly claim to represent? A person may support communication but reject a message written by one government. A nation may support consultation while refusing to surrender control of its own transmitter. A scientist may judge the physical risk to be low while opposing any sentence beginning with "humanity believes." Representation could prove harder than transmission. What language can be called Earth's language? What image represents thousands of cultures? Should the message focus on mathematics and physics? That may appear neutral, yet it presents humanity primarily as a scientific civilization. Should it include art, music, family life, and spiritual traditions. Which examples? Who chooses them? Should the message acknowledge war and ecological damage? Removing those realities creates an idealized portrait. Making them central creates another distortion. Children cannot represent themselves fully in global politics. Future generations cannot vote at all, yet they may be the only people alive when a response returns. The message would be written by one historical Earth and received, if ever, by another. Borders will change. Languages will evolve. Governments that approve the signal may disappear. Perhaps the only legitimate first response is therefore a minimal one. We detected the transmission. This is when it arrived. These are the physical references we understood. We are attempting to interpret the remainder. Such a message avoids claiming that humanity has resolved its divisions. It acknowledges reception without pretending to be a complete planetary self-portrait. Even then, the final moment remains physical. A target appears on the control display. The antenna settles. Power systems reach the required level. The approved file is loaded. Several people confirm that the version matches the public record. Then someone executes the command. Energy leaves Earth. The decision passes from politics into physics. No later vote can recall it. Before humanity speaks, it must confront something no scientific instrument can answer. We may discover another intelligence before we have learned how to represent our own. If humanity chose to reply, the hardest part would not be pressing the transmission command. It would be constructing a signal that could cross interstellar space, reach the correct place, and remain understandable after it arrived. Content and engineering cannot be separated. A perfect message that the target never detects says nothing. A powerful transmission that carries an unreadable sequence accomplishes little more. The response might begin with the simplest possible idea. We received your signal. Even that statement contains assumptions. It assumes the incoming transmission was intended to be received. It assumes there is still an audience. It assumes the idea of a sender and receiver maps onto the system at the other end. So the first response would probably rely on measurable physical relationships rather than ordinary human language. The frequency of the incoming signal could provide one reference. A known atomic transition could establish another. Repeated pulses might introduce counting. Ratios could build toward time, length, and position. Before any of this leaves Earth, engineers must answer a blunt question. How much energy will arrive? Radio waves spread. A transmitter sending equally in every direction wastes almost all its power on empty regions of space. An interstellar reply would therefore use a highly directional antenna or array, concentrating energy into a narrow beam. The larger the transmitting aperture, the narrower that beam can become. A large dish may focus radio energy toward the target system. Several antennas could operate together as a phased array, coordinating their transmissions so that the waves reinforce one another in the desired direction. The target must lie inside that beam when the signal arrives. This sounds simple until the delay is included. For Proxima Centauri, the message travels for a little more than 4 years. Engineers cannot aim only at the star's observed position tonight. They must account for its motion during the journey and the motion of the solar system itself. For a target hundreds of light years away, the pointing calculation extends across centuries. The star's proper motion must be measured. Any uncertainty grows with distance. If the intended receiver is a planet, its orbit adds another moving target. Unless that orbit is well known, the safest approach may be a beam wide enough to cover a larger portion of the system. A wider beam increases coverage. It also reduces the energy delivered to any one point. That trade-off affects transmitter power. Frequency matters too. Lower frequencies can spread into a broader beam for the same antenna size. Higher frequencies may permit tighter pointing, but face different engineering limits and propagation effects. The selected band should avoid heavy human interference and, ideally, use a region the receiver might monitor. Humanity cannot know which frequency another civilization considers obvious. Using the frequency of the detected signal may be sensible because the transmitter has already demonstrated that technology exists there. Another option places the response nearby rather than directly on the incoming carrier, avoiding overlap if the source continues transmitting. The message should not be sent once. Noise can erase a brief sequence. A receiver may not be pointing toward Earth at the correct moment. The target civilization may monitor the band only occasionally. Repetition increases the chance of detection. Engineers would design a schedule. Perhaps the basic acknowledgement repeats every few minutes. A longer message follows. The entire transmission cycle returns over hours or days. Later campaigns repeat it months or years afterward. Each repetition consumes energy and telescope time. It may interfere with other scientific work. Governments and institutions must commit resources long after the historic first broadcast ends. The signal itself needs redundancy. One pulse, then two, then three, a pause. The pattern repeats. After numbers are established, the message could introduce mathematical relationships and shared physical units. Later sections might identify the solar system. An interstellar address cannot use place names. The message could describe the Sun relative to long-lived astronomical objects. Pulsars possess distinctive rotation periods, and a map of several could help locate one region of the galaxy. Nearby stars provide additional references. Every reference changes with time. Pulsars slow, stars move. The map must therefore include an epoch, a way of showing when the geometry was correct. Location and time become one problem. Once the solar system is identified, Earth may describe its structure. One star. Planets in ordered orbits. Relative sizes and periods. The position of the transmitting world. From there, chemistry may follow. Hydrogen. Carbon. Oxygen. Liquid water under a range of temperatures and pressures. Biology is harder. Should the message show DNA? A human body? The tree of life? Earth is not inhabited only by the species operating the transmitter. Humans emerged inside a planetary network of microorganisms, plants, animals, fungi, oceans, and atmospheric chemistry. An honest biological message cannot reduce Earth to one silhouette. A complete representation may be too complicated to decode. Images are not naturally self-explanatory. A receiving intelligence must infer dimensions, orientation, scale, and perspective. Humans understand that a distant figure in a photograph is not physically smaller. We recognize shadows and edges through a lifetime of visual experience. An unfamiliar mind may not. Each picture needs a technical foundation explaining how its units form a grid and what the values represent. Then the political problem returns. What version of humanity should leave Earth? A peaceful version? A truthful one? These are not always identical. Art, music, medicine, scientific collaboration and care for family are real parts of our species. So are war, inequality, exploitation and ecological damage. A message containing only achievements creates an advertisement. A message dominated by failure creates another distortion. Perhaps the first response should avoid autobiography. We detected you. We are located here. We understood these physical relationships. We are attempting to decode the rest. That limited statement reduces misrepresentation. It may also feel unbearably small. The transmitter might never be active again. The beam may cross Earth only once. If this is the only opportunity, some will argue that a technical receipt wastes the moment. The message expands. Mathematics, physics, chemistry, biology, images, music, history, questions. Every layer increases potential meaning and potential confusion. Scientific knowledge creates another dilemma. Should Earth transmit details of nuclear physics, genetic engineering, artificial intelligence, or advanced materials? The receiver may already know far more, or information could enter a society with a different technological balance. Once sent, knowledge cannot be recalled. That does not make communication automatically dangerous. It means the export deserves deliberate thought rather than romantic assumption. The same caution applies to incoming information. A diagram may be a useful design. It may be incomplete. It may describe an experiment requiring safeguards not included in the section humanity decoded. It may not be an instruction at all. A staged exchange would be safer. First acknowledgement, then shared references, then questions designed to test whether both sides interpret those references in the same way. Only after that foundation survives should richer archives follow. Distance makes this careful plan almost unbearable. Proxima Centauri lies approximately 4.2 light-years away. A reply sent tonight needs more than 4 years to arrive. If the receiver detects it immediately, understands it immediately, and answers without delay, the response takes more than 4 years to return. The minimum round trip approaches 9 years. That is the fastest plausible exchange with another star. Reality adds delay. Humanity may spend years approving the reply. The other side may spend years analyzing it. Its transmitter may operate only during limited windows. One question could consume decades. At 100 light-years, the physical round trip is roughly 2 centuries. Everyone who approved the first message would be gone before the answer arrived. At 1,000 light-years, question and response require about 2,000 years. A conversation at that distance is not conducted between individuals. It is conducted between civilizations and their descendants. The technical archive must therefore travel through time as carefully as the radio signal travels through space. Future researchers need to know why each symbol was chosen, which parts of the incoming signal were understood, which remained uncertain. What did Earth ask? What interpretation was expected? What frequency and timing should the returning transmission use? The record must survive software changes, obsolete storage, institutional collapse, war, migration and language evolution. A response may return to a world that no longer remembers the question. The people writing the first message would need to trust generations not yet born. At the transmission facility, the final sequence is checked. The beam calculation includes the target's future position. The power and repetition schedule are confirmed. The approved message hash matches the public archive. The antenna begins tracking. Then the carrier rises. The response passes the moon, crosses the planetary orbits, leaves the heliosphere. No human instrument can follow the individual radio waves through the darkness. For years or centuries, Earth receives no proof that the decision mattered. We continue listening, decoding, arguing, maintaining the archive. Somewhere between the stars, the message moves toward a civilization that may be waiting, may have changed beyond recognition, or may already be gone. Detecting the signal was a scientific event. Answering it would be a physical commitment to the continuity of intelligence across time. Before any response could return, Earth would have to become the kind of civilization capable of remembering one question for generations. And that may be the real test. Not whether humanity can detect another intelligence. Whether humanity can carry the discovery without reducing it to a slogan, weapon, myth, or forgotten file. The first result would be scientifically narrow. A signal exists. Independent instruments detect it from one celestial location. Known human and natural explanations fail to account for its measured behavior. The best available explanation involves technology beyond Earth. That conclusion alone changes history. It does not reveal a face. It does not guarantee a message. It does not establish that anyone is waiting. Most of the questions people care about would remain unanswered. Who built the transmitter? Was the source biological, artificial, or some combination of both? Did the signal come from a planet, a spacecraft, an orbital station, or an automated beacon? Was Earth the target? Was there ever a target? Did the transmission carry language, telemetry, navigation, or nothing more than a stable carrier? The discovery creates certainty at one level and uncertainty everywhere above it. That tension would define the years that follow. Scientists could divide the evidence into 4 layers. The first is measured. Frequency, bandwidth, drift, timing, polarization, source position, repetition, signal strength. These properties come directly from the instruments, though every measurement carries uncertainty. The second layer is inferred. A narrow stable carrier may indicate engineering. Periodic drift may reveal motion. Repeated structure may indicate information. Localization near a planet could connect the transmission to an orbiting source. These conclusions arise from models tested against the data. They are stronger than speculation. They are not raw observation. The third layer contains credible possibilities. An automated beacon, a communication link, a deliberate broadcast, a surviving machine from a vanished civilization, a system still operating inside a living society. Each may fit part of the evidence. None should be presented as fact until it makes predictions the others do not. The fourth layer is unknown. Purpose, identity, intention, whether the sender still exists, whether a translation captures the intended meaning, whether Earth's reply, if sent, will ever be noticed. A mature response would keep these layers visible. Public language tends to collapse them. A confirmed extraterrestrial technology becomes aliens. Structured modulation becomes a message. A message becomes contact. Contact becomes an imagined relationship with motives, emotions, and plans. The telescope never measured those things. This is where the discovery becomes a test of human restraint. Can society hold an extraordinary fact without immediately filling every empty space? Can institutions admit what they do not know while acting decisively on what they do? Can researchers preserve uncertainty without sounding evasive? Can the public remain interested after the first dramatic announcement gives way to years of analysis? The signal would place our habits under pressure. Our appetite for certainty. Our tendency to reward the fastest explanation. Our suspicion of closed institutions. Our willingness to share evidence. Our instinct to control knowledge once it appears valuable. It would also expose the limits of scientific authority. A telescope can establish where the energy came from. It cannot decide whether raw data should be temporarily restricted for security review. Signal analysis can reveal structure. It cannot determine which culture should appear in a planetary message. Physics calculates the light travel delay. It cannot decide whether the present has the right to create obligations for people living 2 centuries from now. No equation produces legitimacy. No receiver selects a representative for Earth. The discovery is therefore both window and mirror. Through the window, humanity sees that technology emerged elsewhere. In the mirror, humanity sees how it behaves when certainty, power, and wonder arrive together. Some effects would appear quickly. Radio observatories receive new investment. Search programs expand. Old datasets are reprocessed with improved methods. Engineers design instruments capable of watching the source continuously. Researchers search for associated optical flashes, infrared excess, atmospheric chemistry, or additional radio channels. Other changes unfold more slowly. Universities create new fields combining astronomy, information theory, linguistics, anthropology, and law. Schools teach the detection as part of natural history. Philosophers no longer discuss technological intelligence using Earth as the only known example. That shift is deeper than any one message. Technology would no longer be known from a sample size of 1. Before the signal, every theory of technological civilization is built from one evolutionary path. One planet, one biosphere, one species capable of constructing radio telescopes. After confirmation, humanity gains a second case. Perhaps the information is limited. Perhaps we know only that a transmitter operated at one location and time. Still, one additional example transforms the problem. Now comparison becomes possible. Did the other technology exploit the same regions of the electromagnetic spectrum? Did it create narrow carriers? Did it use redundancy to protect information? Did it remain detectable for years? Could its source survive long enough to build systems that outlived individual lives? Even silence between transmissions becomes data. A beacon active for centuries would demonstrate durability. A brief signal may indicate scarcity, scanning, failure, or simply a narrow geometry. A transmission powerful enough to cross thousands of light years reveals either immense energy, extreme directionality, or both. A message designed for an unknown receiver reveals something else. Its makers were capable of imagining a mind unlike their own. That insight may be among the most profound. The sender did not need to know human language. It needed to believe that somewhere, sometime, another intelligence might notice structure and attempt to understand. The signal would connect two technological histories without removing the distance between them. No spacecraft currently available could carry humans to most candidate systems within a lifetime. No delegation could stand beside the transmitter and ask what the symbols meant. Earth remains dependent on light. Photons and radio waves, delayed evidence crossing a space that cannot be negotiated away. The telescope becomes the border. On one side, an entire planet building interpretations. On the other, a source seen only through the energy that reaches us. After the announcement, the world may expect a conclusion. Instead, the discovery creates a discipline. Keep listening. Preserve the raw data. Test every translation. Protect the frequency. Watch the target. Search old archives for signals recorded before anyone understood their importance. Prepare future observers to recognize changes the original team will never live to see. The first researchers eventually leave the project. New scientists inherit their calibration notes. New engineers replace the receivers. Institutions merge, change names, or disappear. The source remains in the sky. Perhaps the transmission continues. Perhaps it fades. Perhaps one new sequence appears after 20 years and forces humanity to reinterpret everything. The greatest discovery in history may not end with an answer. It may begin a permanent state of attention. Before confirmation, cosmic silence could still be imagined as emptiness. After one artificial signal, silence acquires alternatives. Distance. Timing. A beam pointed elsewhere. A transmitter between cycles. A civilization that no longer uses radio. A reply already traveling but not yet arrived. Nothing about the night sky looks different. The meaning of the darkness has changed. And somewhere in that darkness, one narrow line has already crossed the distance. Years later, the first image would still look almost too small for what it had done. A dark field. Faint bands of noise. One narrow line leaning gently across a waterfall plot. Students would see it in textbooks. Researchers would enlarge it during lectures. Documentary films would rebuild the moment with music, telescope dishes, and slow views of the stars. But the original evidence would remain quiet. No face. No voice. No visible machine. Only energy measured by an instrument on Earth. The first researchers would grow older beneath the weight of that line. Some would continue studying it for the rest of their careers. Others would move into different fields, carrying the knowledge that one ordinary observing session had divided human history into a before and an after. Before, technology beyond Earth was possible. After, it was part of the known universe. The discovery date would become famous. But the discovery itself would not belong to one date. It would continue every time a new telescope returned to the source. Every time an old observation was reopened. Every time an analyst discovered a weak feature hidden beneath the noise. Every time another section of the transmission became clear. The archive would grow. Original recordings, independent confirmations, calibration files, equipment logs, satellite records, early interpretations, rejected translations, political debates, public statements. The reply, if one had been sent, all of it would need to remain connected. Future generations would have to understand not only what humanity concluded, but how those conclusions were reached. They would need to see the uncertainty, the failed explanations, the moments when confidence rose too quickly, the evidence that survived. An archive preserving only the final answer would not be enough. It would need to preserve the path, because the people who first detected the signal would not remain its permanent guardians. A new generation would inherit it. Children born after the announcement would never remember a universe in which humanity appeared technologically alone. For them, the existence of another source would not be a sudden rupture. It would be part of reality. One star among the stars had produced a machine. One distant system had sent energy into the dark. That knowledge would enter classrooms before many children were old enough to understand why earlier generations found it overwhelming. They might ask questions adults could not answer. What did the sender look like? Did it know we were here? Why had the message stopped? When would our reply arrive? Would an answer return during their lifetime? For a nearby source, perhaps some of them would live long enough to see the next stage. They might be adults when the first possible response reached Earth. They might remember standing outside as children, searching for the source star with their families, then return decades later to watch another line appear on a screen. For a distant source, no living person would expect an answer. The waiting would become cultural rather than personal. Observatories would continue monitoring because someone had promised that Earth would keep listening. The responsibility might pass through institutions that had not existed when the original signal arrived. New telescopes would replace old ones. Receivers would become more sensitive. Analysis systems would change. Storage formats would become obsolete and be converted again. The original software might survive only through preservation projects maintained by people born long after it was written. Even the famous first telescope might eventually stop operating. Its dish could remain beneath the sky as a monument. Visitors might stand near it and imagine the night when data from one source changed the meaning of every other star. The metal would age. Paint would fade. Cables would be removed. But the measurement would continue inside copies spread across the planet. The signal had traveled through space before entering one receiver. After detection, it would travel through human time. That journey would be less predictable. It would pass through changing governments, languages, technologies, and beliefs. Each generation would interpret the event from a different world. The first generation might experience shock. The next might experience responsibility. Later generations might experience frustration. They would know the source existed, yet remain separated from it by physics. Some might lose interest. The signal could become familiar, a permanent fact discussed in schools and remembered on anniversaries. Then a new observation could make it strange again. A second frequency appears. A repeating structure changes. A weak response arrives after decades. Or another signal is found from somewhere else entirely. The first detection would transform every later search. Before it, a strange line could be dismissed as another likely example of interference. After it, researchers would know that at least once, the extraordinary explanation had survived. That knowledge would make caution more important, not less. Every new candidate would attract enormous attention. Every false alarm would be compared with the original. Teams would still need to test cables, satellites, equipment, and local transmitters. They would still need independent observatories. They would still need to resist the emotional force of a promising target. The universe becoming inhabited would not make the instruments infallible. It would make the consequences of error larger. So the work would continue in the same patient way. Point. Record. Check. Move away. Return. Compare. Ask another observatory to look. The most consequential discovery humanity had ever made would become part of a routine built from discipline. And perhaps that would be fitting. The signal did not arrive because Earth was ready. It arrived because a telescope was listening. Because engineers had built a receiver sensitive enough to notice it. Because researchers had created methods designed to reject almost everything. Because someone looked at a narrow line and refused both easy dismissal and easy belief. That balance would remain the heart of the story. Wonder without surrendering judgment. Skepticism without closing the door. The source star would continue to rise above Earth. From one continent, it might appear low over the horizon. From another, it might not be visible at all. People would use different names for the constellations around it. They would tell different stories beneath the same sky. Yet the coordinates would lead every telescope toward one physical place. There, the direction from which the evidence came. The source itself might look completely ordinary. A point of light. Perhaps too faint for the unaided eye. No visible sign of cities. No obvious structure. No proof, from appearance alone, that technology had ever existed nearby. humanity would know the system through delayed fragments. Starlight, planetary motion, spectral lines, and one artificial transmission that crossed the darkness. Perhaps the message would eventually be understood. Perhaps it would reveal a civilization still alive and waiting. Perhaps humanity would exchange knowledge across years, centuries, and generations. Or perhaps the line would remain the only thing ever received. One brief confirmation that intelligence had happened elsewhere. If so, people would return to the recording again and again. Not because it contained every answer, because it permanently changed the question. The cosmic silence before the detection had been empty of evidence. The silence afterward would be different. It could contain distance. A failed transmitter, a beam pointed elsewhere, a society that had changed communication methods, a civilization waiting on timescales longer than human patience, or a message already moving toward us, still centuries from arrival. Silence would no longer prove absence. It would become part of the uncertainty. At night, the telescopes would keep turning. Their dishes would move slowly beneath the stars. Computers would receive oceans of data. Most of it would be ordinary. Natural radio emission, human interference, instrumental noise. Researchers would continue searching within it, not always expecting another historic moment, simply remaining available to one, and somewhere in an archive, protected by copies, explanations, and the care of people who understood its value, the first waterfall plot would remain. A narrow drifting line, a small mark made by energy after a journey between stars. The line would not show the transmitter. It would not show the beings or machines that built it. It would show only that the distance had once been crossed. That was enough. Enough to prove that the universe had produced another technology. Enough to force Earth to examine how it listens, how it speaks, and how it remembers. Enough to leave every future generation beneath a sky that could never again be entirely silent. Once the universe has spoken once, silence can never mean exactly what it meant before.